Good day, everybody. How y'all doing? Good, good, good. All right, good to hear. Hope weekends were nice. I might have lost money in a bet. Thanks, Bengals. But I knew nothing about sports, and I just bet because of the mascot. That one's on me. Any random questions before we get started today?
How do you find it?
Great question. I will definitely be talking about 10, 9, any others that you guys want to look at. Let me get to some announcements first. That is definitely on schedule. Today is Monday, February 14th. Main thing to keep in mind for today is the Chapter 2 homework and quiz are due. So probably the bulk of today is going to be spent looking at some questions related to the Chapter 2 homework and answering any questions and looking at the issues you guys are having. Make sure that you send me any questions you have while you are finishing that up tonight. In class and lab this week, we're going to be studying collisions, namely how collisions involve kinetic energy and momentum, which additionally is to say, we do have normal lab this week, so do come to your assigned day and time as usual. In the near future, though, we will be having our first test in these coming weeks. Now, this class, midterms are coming up, so I wanted to mention test is coming up and to kind of differentiate between test and midterm for the sake of this class. Midterm grades are coming up, and in this particular class, we don't really have a dedicated midterm assignment. There is the first test, which just happens to be around midterm time. And for this class, midterm just serves as me calculating your grade and telling you what it is, like your average for the whole class. It's not how did you do on one test, it's just your current total grade in the class, and that's going to be what you see for your midterm score. So it's just a check-in for this, for my class at least. It's just, are you passing? How you doing? You can ask me questions about any part of your grade if you want to. So we will have a test by the time midterm scores go out. It's not necessarily the midterm test, it's just test 1. Test 1 is going to be either first or second week of March, depends on how the learning this and next week go. And the way that it works for this class is you will, on your lab day, you will come to this room and you will take the test during lab time. There won't be a lab in addition, we just do it instead of lab. And I like doing it that way so that you don't have to rush here at the start of class or rush out to get to another class. You just have the lab slot to take a 1-hour test in as much time as you need. And that will be either first or second week of March. It'll be plenty of time for me to get everything graded and get the midterm scores in and calculated and sent out, so that that test is factored in to that midterm grade. This week we're doing chapter 3, which is collisions. Next week we're doing chapter 4, which is rotational motion. And then test will be in the weeks following. So on chapters 1 and 4, I do create study guides for tests as they come up. I'll make a list of all the topics that have been present in chapters 1 through 4, make sure that it's labeled on the formula sheet, which formulas will be involved in those chapters, which ones you don't need because they're for later chapters. And I post practice questions that are just non-graded practice that you can optionally do if you want to, new questions to work on. And I post an answer key so that you can check your answers to that work as you're studying. All of that will probably be available by the first week of March, and then we'll probably do the test itself second week of March, is what I'm currently thinking. How do all of these announcements sound to you at this time? Okay, nodding, good. After test 1, we'll move on to the next batch of chapters. Test 2 will be about chapters 5 through 8, which will start being more about energy and like history and stuff. So, to move on to the meat and potatoes of this day's activities, let's look at the questions related to the chapter 2 homework that I know you guys already have. We've already had one person ask about 10, and I want to talk about 9. If for no other reason, then 9 is a very good example of what we're actually going to be doing this week. So I want to make sure to step through that with you guys to help set up lab and lecture for this week. But we're going to start with 10, because it's what's currently on screen. 10 is a power question, and it involves daisy chaining a couple of steps and assumptions one after the other. I would say that 10 is probably the most, I would call 10 the hardest one on this assignment just because of the number of assumptions that we've made and the number of formulas that play into those assumptions. But I want to step through that logic with you now. We have a dog sledding team. There's 4 dogs pulling one human. We know the mass of that human. And that human is riding a sled. We know the mass of that sled. That means that the dogs are pulling the combined mass of sled and human together at once. So ultimately, we're going to need to add those 2 masses together. Whatever your numbers are, the masses need to be added. That's the total mass the dogs are pulling. We have 4 dogs pulling this combined mass. I haven't seen anyone's number of dogs differ. I assume that's a constant 4. But some number of dogs all working together. And they are pulling the sled at constant velocity across the snow. Constant velocity, you do know that velocity. It will be a number given to you. And you are also told coefficient of friction between the sled and the snow. So, the list of things that we know is, I'm going to list combined mass because I'm going to guarantee you we don't need the 2 masses separated. We need to know the total mass that the dogs are pulling. 80 plus 22.2, at least for my sample numbers, it's going to be 102.2 kilograms. We know number of dogs. They equally share the work. That will become relevant at the end. We know constant velocity of 8.9 meters per second. If velocity is constant, that means acceleration is 0, which also tells us that net force is 0. All the forces present add up to 0. That will be an assumption we need to make. And the coefficient of friction, which is mu, the weird looking Greek letter M, is 0.12. That one doesn't have a unit, it's just a number. And the thing we've been asked for is power, the power output of each dog in this activity. So, let's look at the formulas for power. There is 2 of them. We want power. The 2 ways we have defined power are either work divided by time or force times velocity. Which version do you think will be more useful given the things we already know?
Force times velocity.
Force times velocity. We already know velocity, which means we just need to figure out the force that the dogs exert. So I'm going to further label this force dogs. Because the dogs are what's exerting the force in this situation. So, we need to figure out the force the dogs as a whole, like all 4 dogs combined, exert. So we'll multiply that by the total velocity, and that will eventually tell us the power that we're after. So, let's examine the forces on this sled. On Earth, gravity must be pulling down, and since we can assume that this is on flat, level terrain, normal force must point upwards, because we're not accelerating downwards into the snow. The ground must be supporting us. Dogs are definitely pulling forward. There's force dogs. And since we were told that there is a coefficient of friction for pulling forwards with a force, but we're not accelerating, there must be some force of friction opposing the force that the dogs exert. So all four of these must add up to zero. That's the only way we can be moving at constant velocity and not accelerating. Since they all add up to zero, normal force and gravity are the only two vertical forces. They're off on their own and they cancel out. That means that the force of the dogs must add up with the force of friction to become zero.
Would
Yes.
that be like the mu thing?
The mu is factored into this, yes. Does that answer the question?
Yeah.
Yes, I'm going to put all the relevant formulas on the board in a second. Force of the dogs forwards must be equal and opposite with the force of friction for them to add up to zero. So I am going to write net force dogs, plus force of friction must equal zero. Ultimately, this means that force dogs is equal and opposite to the force of friction. So if we find out the force of friction, we can find out the force the dogs are exerting to counter the force of friction. Which means we need to look up what the force of friction is. That formula is normal force times mu. We know mu, question tells us mu, which is fantastic. Mu is the coefficient of friction between the sled and the snow. So that is already a known number. Which means the only other thing we need to calculate the force of friction is normal force. We need to estimate what the normal force the snow is exerting upward on the sled is. And based on this picture, what can we assume that the normal force is equal to? The force of gravity. So it's not equal to 9.8 itself, but it's equal to the weight of the sled. And we will use 9.8 to find the weight of the sled. Or rather, the weight of the sled and the human combined. They are functionally one object right now. So, normal force is equal and opposite to the force of gravity in this situation, and that's going to equal the combined sled and human mass times 9.8. So, I mentioned that this does involve some daisy chaining assumptions and formulas together. So, going now from the end of our logic back to the start of our logic, the steps that I recommend are, 1, calculate the combined weight of the sled and human together. That's why I added their two masses together. So total mass is what I've written here. Total mass times 9.8 tells you the weight of the sled, which will also tell you the number for the normal force in this case. That number can be used with your coefficient of friction to find the force of friction. That force of friction is equal and opposite to the force the dogs exert. So that number can be put up here with your velocity to find the total power output of all four dogs working together. I'm getting some glances that I might be registering as confused or concerned. How does this feel?
Seems like too much information.
Possibly, yes. This is designed to be the tricky one of this 10 question set, the one that requires the most amount of assumptions. There is one more trick, one more thing. Because if you do this in the reverse order I mentioned to get to power, this would be the power output of all four dogs together. You've been asked power output per dog. So using this method, whatever you get for power, you need to divide by 4. Like I said, this is the tricky one. real quick though. I will show that this method works. I will show that this works, to show that I can get to this final answer. Normal force is total mass times gravity. Normal force times mu is friction. That gets plugged in for force dog. So power combined would be combined mass times 9.8 times mu times velocity. That's the combined thing together. Normal force times mu, the force the dogs exert, times the velocity, total power. Using my sample numbers, that's 100 times 2.2 times 9.8 times 0.12 times 8.9. So to prove that this works, 2.2 times 8.9 is the speed at which the dog is pulling. That comes out to 1,067 watts, which again is all 4 dogs at once. This number divided by 4 is 288. 268, pardon me. I have this thing where the correct number is in my brain, and the mouth refuses to say it. It especially acts up when I'm trying to tell someone what time it is. That'll work. Yes. So, a lot of assumptions, a lot of chaining, but it works. Scout's honor. How does 10 feel?
I was doing it like the way that way, on the right side on the board,
Mm-hmm.
and I got 1,056.
Okay.
So I'll plug that in for force of friction for the next formula, and I got 120.1872.
Okay, that would be the force that all 4 dogs are exerting together at once. That is the force of friction, and they must exert the same equal force to oppose it. You then need to multiply that by whatever your velocity is for the dogs. So if you were to multiply that number by 8.9, you should get this number. I will check that though. 2 times 0.8 times 0.2. Yeah, I got 120. 120 times 8.9 is, oh, I wrote this down slightly wrong. Actually rounds up to 170. And 170 divided by 4 is, rounds up to 268 approximately. Okay. Like I said, this is the tricky one. How do you feel? Alright. I would like to look at 9 now. But definitely, at minimum, want to cover 9 with you guys. Because it sets up the rest of the week. This. Wow, it randomizes the numbers every time I reload the question. That's inconsiderate. So, 9 is a momentum, impulse, and collisions question. I specifically mentioned this when we were talking about impulse on Friday, but I want to, momentum and impulse on Friday. And in this example, we have a baseball of known mass being thrown through a window. Looks like the mass was unchanged at least. So, let's look at the physical situation. Ball is thrown at a piece of glass. Ball is going to break that glass and continue traveling through the hole that it makes to the other side. What will happen to the ball's velocity during this process? Say again? It does get lower. The ball's velocity is going to drop. Whenever you crash through something, you are going to slow down as a result of that. But frankly, you don't even have to crash all the way through something. Hitting something tends to slow you down. I know this because I've been skating more than once. So, and we know the velocities. We're told the velocities. We have the initial speed of 11.3 and the final speed of 8.63. So before we pass through the glass, we are moving faster than after we pass through the glass. So we definitively slow down in this interaction. This happens because the ball is going to exert a force on the glass, and that's why the glass breaks. But due to Newton's third law, the glass also exerts a force on the ball. And that force, as the ball moves forwards, the glass forces it backwards. That's going to cause it to slow down. If something's moving forwards and you force it backwards, that's going to decelerate it for as long as that force is applied. It's like hitting the brakes. So the ball slows down. Because it slows down, because its velocity changes, its momentum is going to change. Anytime velocity changes, momentum will change, because momentum is mass times velocity. So since velocity changes, momentum changes. The ball has less forward momentum because it's moving slower. Anytime there's a collision, the colliding objects tend to swap around their momentum. Momentum is kind of like energy in that it can transfer between objects. If you've ever, there's a desk toy called a Newton's cradle. It's the like steel balls that are hanging, and if you pull one of them back, it hits the others, and then the ball on the other end moves, and then that keeps continuing back and forth. That is an example of momentum transferring in a collision. The ball on the end collides with the collective, and its momentum transfers through the rest of them into the last one. So in this collision, the momentum, some of the momentum, not all of it, but some of it is going to exit the ball and enter the glass. And now that the glass has momentum, those shards fly outwards. They have momentum, now they're going to move. And so that's what happens to the momentum of the ball. Some of it exits the ball and enters the glass. And the glass breaks and the shards fly everywhere. And that's why the ball's momentum drops. It just has less now because some of it is now in the shards. Momentum changed, therefore it underwent an impulse. Change in momentum is just called impulse for reasons that only Isaac Newton knows. And since, well, we can calculate that change in momentum, which means we can calculate the impulse. Now, when something undergoes an impulse, whenever it changes momentum, we call that undergoing an impulse. And since, from the baseball's perspective, it hit the glass, and the glass is what slowed it down, the terminology here is that the glass imparted an impulse onto the baseball. Lingo's a little weird, I admit. Ultimately, though, in this collision, there is an impulse. The ball has an impulse, its momentum changes, and the first thing we've been asked is, what is the direction of that impulse? Momentum is a vector. Momentum is a vector because velocity is a vector. And so if you have forward momentum, it wants you to keep moving forwards. The ball has forward momentum in both of these cases. It's still moving forward. Its velocity is still positive, so its momentum is still positive. But its momentum, its forward momentum, does technically drop. is I'm actually going to, using my sample numbers, calculate that initial momentum and that starting momentum real quick. Its mass times its original forward velocity of 11.3 is approximately 1.64 kilogram meters per second of momentum, and its mass times its final velocity of 8.63 gives it a final momentum of approximately 1.25 kilogram meters per second. Its forward momentum dropped. It was moving forwards, it's still moving forwards, but it has slowed down. Some force pushed it backwards in the negative direction to drop its momentum. That backwards force came from the glass. The glass is going to push it this way since the ball is pushing this way on the glass. And that negative force, since if that direction's positive, the force from the glass would point in the negative x. That negative force creates, from this frame of reference, a negative impulse. The impulse points this way because the force involved points this way. But additionally, I can prove a different way that the impulse is in the negative direction by actually calculating the change in momentum here. Impulse is change in momentum, and change in anything, delta anything, is always final minus initial. And our final is smaller than our initial. So 1.25 minus 1.64 will give us a negative answer. And that should be 0.39, I think. Yeah. But very specifically, negative 0.39, because of the way that, because we subtracted a larger number from a smaller one. The impulse being negative means that the impulse pointed in the negative direction. It's a vector, so it does point in a direction, but it mainly just means that the glass took momentum away from the ball. And so ultimately, to answer the first question asked in number 9, what is the direction of the impulse the glass imparts to the baseball opposite the direction of the ball's motion? The ball's moving forward but slows down because of this impulse. That means it points, and if the ball's direction is positive, the impulse points negative. The impulse on the ball points negative. The second thing you're asked, I've also already shown how to find. First question is just the direction of the impulse. Second question is calculate that impulse. One thing to note though, Achieve doesn't care at this phase that the impulse is negative, because it already asked you what direction it was in. Now it just wants the number. And whoever coded this question did not code it to receive a negative answer. It's been coded to accept just the positive absolute value of magnitude of the answer. So note, the answer it's expecting here, positive 0.389, is basically the absolute value of what I just calculated. So it just doesn't want the negative sign because we already addressed the direction in the first part. I know that Achieve has been kind of fiddly about negative signs on some of its answers at times. And that is because no matter how smart a piece of machinery or code is labeled, it's still real dumb, because it can't learn, it can't adapt, it can only do what it was programmed to do. And sometimes Achieve was just coded poorly to expect or to receive positive or negative answers. It can't adapt to the situation based on the frame of reference that you create in your own question, which I would be able to read your work and tell what your frame of reference was. But this thing is inflexible and dumb. It can't learn. So occasionally it's going to make mistakes, and when it makes a mistake, like if you think to yourself, I am doing the right thing, I've been inputting my correct answer in every form I can possibly conceive, and it's still disagreeing with you, I want you to email me. Because I can look at the answers you submitted and look at your work and see if you did it right, and I can manually change your score. If the chief is acting up, I want you to tell me so that I can fight it myself. Now, my pro tip for parts 2 and parts 3 of number 9 on this assignment is, technically speaking, the answers are negative, like they point in the negative direction, but a chief doesn't want the negative sign in these answers. It just wants the positive opposite value number. How does second one feel for right now? All right, that is the impulse that the glass exert imparts onto the ball. The third part introduces a new piece of information that you did not previously have. You've been told the length of time that the collision lasts. My sample numbers here are 10.5 milliseconds. That is milliseconds, not normal seconds. Yes.
Yeah, I missed so many of my questions because I didn't know what MS stands for, and I kept missing a bunch of it.
Okay, if you send me an email, I can double check and reset the points, because I don't want it to cost you things because of that.
Yeah, I was like, I was like looking up on Google and stuff. I didn't know what MS stands for.
And I imagine you can get any possible acronym from that. Sorry about that. Yes, this is milliseconds. Ball is in contact with the glass for 10.5 milliseconds. And milli is the smallest metric prefix that we regularly use. Kilo, hecta, deca, base, deci, centi, milli. So to convert milli back into base, you need to divide by 1,000, or alternatively, rabbit hop decimal point 3 places to the left, and that would give me 0.0105 seconds. Very small amount of time. And this is the time that the collision lasts. Every single collision only lasts for a certain finite amount of time, and it's usually too small an amount of time for the human eye, ear, and brain to adequately process unaided. But if you, like, slow-mo, freeze-frame camera any collision, and I recommend watching some Mythbusters episodes for this, it's really cool to see what they do sometimes, you can see and measure the amount of time the two objects are in contact and the amount of time that a collision actually lasts. And it is always a finite number, usually a small one, but it is a number that can be measured and used in a formula. And so in this case, the collision officially lasts for this amount of time. That is the amount of time that the two things are touching. That's the amount of time that there is a force applied between them, because they can't exert a force if they're not in contact with each other. And we've been asked, what is the force that the glass exerts on the ball in that amount of time? Because every collision not only lasts such an amount of time, but there's also a force involved in that collision. I don't recommend it, but if you've ever punched glass, you know there's a force involved, you feel it on contact. All collisions involve forces. And the way to work this last case is actually to use the other formula for impulse, which I did show in the notes, but we haven't used it in class yet, which is why I wanted to address it here. Impulse is change in momentum, which can be found with mass times change in velocity, but can also be found with force times time. Every collision has some amount of force in it, and it always lasts a fixed amount, not a fixed, but a finite amount of time. Multiply that force and time together, and that tells you the impulse involved in that collision, the change in momentum of the objects involved in that collision itself. And in this case, we've already figured out impulse, and we've just been told time. So J equals Ft. J, we know T, we can solve for F. Using my sample numbers, impulse is negative 0.39, solving for force. And time, again, you can convert into standard seconds first. And you will get, oh, the answer's on screen. A small-ish amount of force, comparatively speaking. About 40 newtons is enough to break glass. One more thing to note about achieve in this case. Like I said, it wants a positive number. If I keep the negative sign on my impulse, which again just means direction, it points in the negative x, then the force I get out is also negative because ball's moving this way, ball pushes this way on the glass, therefore the glass pushes the opposite way on the ball. So the negative answer indicates just the negative direction of the glass exerts this force in. But achieve doesn't want that negative because we addressed the direction in the first part of the question. How do we feel? What do we feel? All right. Any complaints, concerns, opinions, haiku? Keep asking me. No one ever has a haiku for me. All right. I'm going to open the floor up to any other homework questions you guys have. I just wanted to make sure to spend some time with this one because it very much sets up what we're doing in lab and class for the rest of this week. This lecture and lab this week is collisions, which this is an example of. So, any other homework related inquiries for today?
I did my division to find the J. I did meters, parentheses, final velocity minus initial velocity.
That should work. Also, it's mass times.
Yeah, mass
change
is
velocity.
yeah. That's
But yes, that should work. Any questions about this one or any others? Okay. I've been asked about 2, but I think we've already covered 2 in this class. This is 9. Also got asked about. So that one. Okay. Excuse me. No questions then? Okay. Homework is due tonight. Make sure to send me any questions you have as you're finishing it up. I will answer them swiftly as I can. And I would like to, before we break, we don't have much time left, and I want to keep you. Want to at least set up the official start of chapter 3. We're going to be examining collisions. We're also going to talk about the full explanations of gravity a little bit this week, because it's going to continue coming up next week. So, the baseball breaking of the glass is an example of a collision. And in all collisions, whenever one object impacts another one, there is going to be some exchange of momentum. Like I mentioned with the Newton's cradle desk toy earlier, one ball hits the others, and its momentum transfers into the other ball in the end. All collisions involve an exchange in momentum. And this is because identical to energy, where we already talked about the law of conservation of energy, where energy can't be created or destroyed, It has to continue existing, it just has to transfer. It can transfer between objects, it can transfer into states we can't readily measure, but it still has to exist, it still has to be present. Energy in collisions can be hard to track, because energy has a bunch of different forms, it can go a bunch of different places. And so, there will be some collisions where, yes, the energy must still exist, like the kinetic energy that the objects bring into the collision, that energy still exists somewhere, but we don't really know where it is and we can't really measure it because it's changed into a different state. For example, I hope you've never witnessed a car crash, but if you say watch an episode of Mythbusters where they have a remote control car drive straight into a wall, that car has kinetic energy before it hits the wall. After it hits the wall, nothing's moving. Where did that kinetic energy go? Say again? To the wall. Yes, some of it goes into the wall. And it can occupy a bunch of different forms. Since nothing's moving anymore, it's not kinetic energy anymore. It must have transformed into some other state. And some common states that energy can occupy after a collision include, but are not limited to, thermal energy, because crashes involve a lot of friction, they're going to generate a lot of heat, and sound. Because sound, which we'll talk about even more at the end of Phys1000, sound is moving air, like air vibrations traveling from the source into your ear. And that means sound takes energy to create. So any crash that creates a loud bang, literally some of its energy had to create that sound. So a ton of the kinetic energy involved in that crash literally is in the air in a form we can't measure anymore, other than hearing it. So energy, because it can change states, is really hard to track in a collision. It still exists, we know this from the law of conservation of energy, but sometimes it's just, we can't detect it anymore. But momentum, you can detect, because it has no other form it can occupy. The kinetic energy in a collision can turn into anything, but momentum can only exist as momentum. It can't transform. It's just momentum. It's stuck. It can swap between objects, but it can't turn into something else and vanish. Therefore, like we have the law of conservation of energy, we also have conservation of momentum. Whatever momentum is currently within two objects must still exist after they crash in the same amount. Again, the Newton's cradle desk toy, if there's 1 kilogram meter per second of momentum in the first ball after it hits the other ones, the other ball must have all of that momentum if the others aren't moving anymore. All of the momentum is accounted for. Whatever the total momentum is at the start must equal the total momentum at the end, across all of the objects involved in a collision. And this is technically true, not just of collisions, but also in explosions. Because explosions are technically a form of collision, even the ones involving like dynamite and fire. If you think of like one of those Mythbusters car test crashes where a remote control car is driven straight into a wall, everything, it's moving, and then crash, it stops. That's a case of going from high speed to low speed. An explosion is the opposite. There's one object at low speed, and then suddenly after the explosion, all of its pieces are scattering at high speed.
Like a firecracker, right?
Like a firecracker, exactly. But all the momentum of all the individual pieces still adds up to the momentum that there was originally. It's just originally there was 0, because nothing was moving. After the explosion, the momentum still adds up to 0 because the momentum of each individual scattered piece is in a bunch of different directions. So if one object splits in two in a collision, in an explosion, and the two halves are racing away from each other, since momentum is a vector, those two can still add up to zero. Since it's a vector, you care about direction, you care about the positive or negative of that direction. Explosions are technically collisions, and therefore they also observe law of conservation of momentum. We'll look at some mathematical examples of that during this week. The thing that I want to end on, because it will be relevant in lab this week, as we start studying collisions and start seeing what happens to the momentum and the kinetic energy in those collisions, I want to mention to you that there are two types of collisions. And there's two types of the broad category of explosion and collisions combined. The two types of collisions we're going to be studying are elastic ones, which is to say, quite literally, bouncy collisions, where things tend to bounce off of one another, like basketballs and things of that effect. And inelastic collisions, where things don't bounce off of each other because they crush and stick together. An example of an elastic collision is throwing a very bouncy ball at the floor. You throw it down, it bounces back upwards. It keeps its energy in that collision, and so elastic collisions are inherently more energetic, more bouncy. Things tend to keep moving after you have an elastic collision, like bumper cars. There's too many similar terms here. Inelastic collisions are different in that if the materials involved aren't bouncy and the objects don't bounce off of each other, like, for example, a remote control car slamming into a stationary wall, that's designed not to bounce back off of the wall. It's designed for the front end to crush so that the car stays in place after the actual crash. That's designed to be a non-bouncy, inelastic collision. And in those types, the energy is not conserved, and it's designed by intention to be less energetic, less bouncy. It dumps all the energy someplace else so that it doesn't end up in the spines of the people in the car. These are the two types that we will continue to study and distinguish between during the week. How do we feel thus far? All right. Lab this week. If you have lab on Mondays, I will see you later today. Regardless of if I see you later today or not, I hope you have a wonderful day and week and month. I'm rambling. Don't let that stop you.